Okay, standard enthalpies of formation, chapter 8.5. So we did all this homework problem today. We had all these problems, 3 or 4 equations, and we rearranged them and did all this stuff. And, it's starting to get kind of tedious. Turns out there might be a little bit easier way to get these delta H's of reactions that we can't get in a bomb calorimeter. That's what today is about, okay? Now you should have already been reading some of this, okay? But here's sort of the rationale behind standard enthalpies of formation. Oftentimes it's called the heat of formation. And this is a standard enthalpy of formation of a substance denoted delta HF with a little sort of Celsius little symbol, that little superscript circle. It's the enthalpy change for the formation of 1 mole of a substance in its standard state from its component elements in their standard state. So today, if we would have taken 2 carbons and 2 moles of carbon and 1 mole of hydrogen and flipped this bottom equation over here, if we would have flipped this equation around, that would be the standard enthalpy of formation for acetylene. Okay? So from its core elements, 2 carbons plus a molecule of H2 gives 1 molecule of acetylene. And that number, which we got, negative 226.7 kilojoules, is the standard enthalpy of formation for acetylene. And so now we can actually go take that number and put it into a data table. So now we have some information that we can probably use on any reaction. Okay? Give you guys a second to write that down. So again, think about that. Once we get the formation of different compounds from their base elements, and we create a few rules, we can kind of start plugging those into these equations and just take and add up all the numbers. So it actually is quite a bit easier. So, you'll see a few people writing. Good, I'm going to move on. And one of the reasons this works really well is because we do something. We say, hey, the standard enthalpy of formation for a pure element. So that means the guys on the periodic table and the gals. I'm sure some of them are female too, huh? I shouldn't be sexist. Probably some are male, some are female. Like copper is clearly female. Has like a female symbol. So it must be female. All of those elements up there, like H2, that's the basic quantity, its standard enthalpy of formation is 0. What's the standard enthalpy of formation of francium? It would be 0. Okay? So they're all set to 0. So if you can break equations down on how they form and you get that data, now all of a sudden you're in business. Okay? So keep that in mind. Whenever you see something like water is not 0, but oxygen gas is 0, H2 gas is 0. Radon is 0. So let's see how this is. And so you'll get a table. You'll see that looks like this. And they'll start listing the standard enthalpies of formation. And then they'll say, 0, F2 gas. Let's see, is acetylene on this one? No, it's not. This is just one I pulled up from, because it was easy. But what I will say is you have actually a better table in your textbook on page 209. Better table. Okay? Much better table. In fact, I've added one up here just because when we do a practice problem, you'll need that number. Okay? I've added one. Okay? So, using delta HF to actually calculate the delta H for a reaction. Okay? I'm not sure. I don't think that needs to be there, that little symbol. I'm going to get rid of it. It's not supposed to be there. Using delta H of formation to calculate the enthalpy change for a reaction, the law of summation of heats of formation basically states that the enthalpy of a reaction is equal to the total formation energy of the products minus that of the reactants. Products minus reactants. This is the key phrase you have to get out of this. Products minus that of the reactants. Okay. So if for every one of the elements and molecules in a chemical reaction, we can get a number from a data table. We can put them and then actually just go do some simple subtraction and addition and get our delta H for that reaction. It's pretty straightforward. Okay? There is the equation.
There's supposed to be a circle thing on that delta H2 or no? No.
Yeah, I don't know. Maybe it is. I'm not sure. I'll have to double check. I always thought that maybe for this, because a lot of times you just write delta H. Okay, let's look at this. This isn't my forte. I'll be honest with you. Yeah, in the text they just put delta H for reactions, not that. So it's possible. I borrowed parts of this and I kind of cobbled this together with some of my stuff and then from another talk. I actually think that these aren't necessarily supposed to be here. Could be that this might mean for 1 mole or something like that. So it doesn't really matter. I mean, as long as you get the idea that really what matters is whether there's an F there or not, okay? But what they're saying is if you can add up all of the heats of formation for products and then subtract them from the heats of formation of reactants, you'll get your enthalpy for that reaction. Notice this is a mathematical symbol, meaning the sum of, and M and N are just your coefficients. So those are your molar coefficients. So you have to take into account molar coefficients in a reaction because on the table, everything is for 1 mole. So if you have 4 moles of ammonia, you have to multiply that number by 4. Okay? So I'll let you guys copy this down. But then I think really when you see actually the example, it becomes a lot more clear. It becomes a lot more clear. And this kind of concept, products minus reactants, use that a lot in acid-base products over reactants. So you got to get used to knowing that. And of course, the mistake that's always made is someone does reactants minus products, and they get the exact wrong answer. Okay? Looks good. I will move on. So, why use delta H of formation to calculate delta H's when we can use Hess's law? I kind of talked about this, but I'll give you a few reasons. Simply put, it's easier. We'll see if it's easier. Finding combinations of reaction to fit your particular reaction begins to get more and more tedious. Okay? So remember that 4th problem that I showed you yesterday? They had, oh, you might need to use these 4 or 5 reactions. So it's like, oh, okay. Thanks. Okay. And it turns out that, there's been hundreds of thousands of chemists before you guys who have actually created data tables, you can look it up, that give very good delta H of formation values for all sorts of different chemicals. So obviously if they're cutting edge of research and you're making new chemicals, you might have to use Hess's law, but if you're doing more simple reactions, you should be able to look these numbers up and then be able to figure out, kind of something you would like to know. I mean, I actually did use this from time to time. I looked up formations because I'm wondering, is this reaction going to be exothermic or endothermic? It's kind of a nice thing to know. Because if you have something that, it's exothermic, the last thing you want to do is hook it up to your heating plate and heat it even more. So when I was in grad school, I was working with some compounds that were benzene rings with nitros, diamino dinitro compounds. I looked at them, and a grad student, a smart postgraduate student, a postdoc who already had his doctorate, came up to me and he says, you might want to think about doing reactions to that compound a little bit. I go, what? He goes, well, dinitro, 1,2-dinitro, 4,5-diamino. He says, have you heard of TNT? Yeah, well, that's trinitrotoluene. Actually, the chemical there is dinitro, but then you got those, whatever. And so I actually did some research and found out, the compound can be explosive. So that meant I'm using an ice bath to do the reaction rather than heating it up. And I actually went and looked and got some values for, if I had a mole of it, how much energy would it release? Is it a negative or positive? And he found out it was highly negative. So it's like it's going to go on its own. You don't need to give it help. You want to actually slow it down. And we can actually create baths that are minus 78 degrees centigrade like that. We take acetone and dry ice, minus 78, cool the reaction down, do the reaction, let it heat up slowly on its own, and monitor it. So these are really useful things. And the best part is pure elements are 0. It's always nice when you're doing math and you can use a 0, right? 10 plus 0, 0. Okay. So this is we'll show an example here. Okay. So let's do a practice problem. Oh. Close your eyes. And water. So again, ammonia plus oxygen gives nitrogen monoxide and water. Okay? So what I want you to do now is we're going to go ahead and see if we can figure out, okay, how to calculate the delta H of this reaction. So now it looks like everyone's got their data and is working on the problem. So we'll go back to that slide. Okay. Still see a few fingers punching calculators, so I'll wait. I'll put the first one up. So what I did is I got number 45.9. Remember, that's kilojoules per mole, right? So if I put the units here, it'd be kilojoules per mole. We just did a big thing with the regular kids about it's called the crash of Flight 143, and it was about how some bozos filling up the fuel tank didn't put the units. And they said, what's the conversion factor for liters to kilograms of fuel? And the guy said 1.77. And they all took it, and so they first figured out how much they was left, and then they used that same conversion factor to figure how much they had to put in. Well, they actually was using the conversion factor of pounds per liter, not kilograms per liter. Kilograms are 2.2 times. A kilogram has 2.2 times more mass than a pound. So they actually ended up needing 20,000 kilograms or 20,000 liters of gas for their trip, jet fuel. But unfortunately, they only put 4,000 in because they were using the wrong conversion factor. So if I was a good teacher, I would have put kilojoules per mole, and I would have put moles here, and then you'd cancel the moles, and that would be kilojoules. So your final answer would be in kilojoules. But I didn't, primarily because it was hard to put all this on the slide. But look at 4 times negative 45.9, 5 times 0. I actually took the time to write 5 times 0. That's kind of silly. 4 times 90.3, 6 times negative 241.1. So this is what I ended up doing. I got 183.6 plus 0, 361.2 plus that. I got negative 183.6 for the reactants, negative 1,089 for the products. And then you go products minus reactants. I got negative 906 kilojoules. Did I do it right? What do you think? Did I do it right?
Yes.
Do you all get, how many people got the right answer? Raise your hand. Okay.
I got pulled up the wrong thing. Like on the table, I looked at the wrong thing for O2. Because there was
O3 or O?
Yeah.
Yeah. Elemental, it's always 0. Okay. O3 ozone is not it's pure element. Okay. So that's all you do. Now, yes.
For the NH3 was the number different on the data table?
Maybe I did. Did I really?
Yeah, it's 26.1.
On the data table?
Yeah.
It's only a 0.1.
Oh.
Difference.
Either I made a mistake on one or the other. I don't know which. It's funny they didn't have ammonia on there. In your textbook, they actually have the for ammonia, so I just added it on. Okay, so you say it's what is it? 46 point. What did I have?
46.1.
It's quite possible that this person did it, and on their table they had 45.9. It's quite possible another table is 46.1. Not out of the question. Okay, so you definitely will see the slight changes in values on different tables. Okay. The other thing to keep in mind, that table, there were some assumptions made. The assumption was, again, 1 mole. The assumption was also 25 degrees and 1 atmosphere pressure. So these do change, these formations, with different pressure and temperature. Okay? So that might be some, but it turns out that the changes are pretty small. Okay? There you go. You guys got about, just enough time to write it down. So problems 38. Just don't forget to add the delta H in the equation, and then 39, 43, 45. Chem dollar problem. Number 52, you get a couple bucks if you want to try it. A little more challenging, might work your brain a little bit more. This is due on Monday. It's homework number 74. It's up here. Write down homework 74 as well.
This is 74.
This is 74. Okay?